Thank you very much. Can you hear me? I think you can hear me. Thank you. So thank you very much for the invitation, and it's a pleasure to be here at SGP. I think last time I gave a talk in a grad school, it was 5 years ago, so it's been some time. So I would like to talk today about what we call geometric deep learning. So it's basically it's an umbrella term to actually two things: application of deep learning algorithms to geometric data, and also trying to incorporate geometric knowledge and geometric models into machine learning algorithms, not necessarily applied to 3D data that we encounter in these applications. So it's a much broader topic, and I will show only a subset of it. So how many people here have not heard of deep learning before? Well, I guess nowadays it's almost a household term. And if we look at the history of what nowadays is deep learning, or in general machine learning, it actually has very long history. The first works date back to the end of the 50s, works by neuroscientists, and it actually went through some periods of hypes and despair, what is called the AI winter by some people. And basically it is coming back very strongly, and now it has already become a successful technology that is used in many commercial products. And you have probably heard about AlphaGo, a Google program that won the Go champion, and basically many other applications that use these kind of methods. So this is one of the fields where deep learning has had probably the biggest impact is computer vision and image analysis. And if you look at the performance of different methods on the famous ImageNet benchmark, which is a classification of images, a challenge that consists of about 1.5 million images that need to be classified into 1,000 different categories. So you can see the performance that preceded the use of deep learning, and the performance that we are able to achieve now. It is already better than human performance. It's about 2% error. So this benchmark is almost not interesting anymore. And basically, deep learning was the kind of methods that brought the breakthrough in this challenge in 2012. And now, if you go to a computer vision conference like CVPR, and if you compare it to how it looked like a decade ago, you will not recognize the conference. First of all, it's several times bigger, and also the methods and the kind of people attending it are completely different. Now, historically, the way that people approached image analysis problems in computer vision was basically trying to come up with some handcrafted features. So there was actually a plethora of algorithms nowadays probably almost forgotten, like SIFT scalar invariant feature transform that allowed to detect key points and extract some local description of an image around these points. And then these features would be collected and passed to a classifier, usually something simpler like a support vector machine. And that classifier would predict whether this is a car or something else. So today with deep learning, it is possible to train an end-to-end model that is generic and is trained on the data. And actually, when talking about neural networks, it's probably already not correct. I think now the discourse in machine learning community is about differentiable programming. So there are actually very well-developed frameworks that allow you to take more or less any computational graph and basically learn on this graph. So basically, you can, if you can write your algorithm in a way that you can backpropagate through it, basically you can incorporate it into your learning architecture. So it doesn't need to be necessarily a neural network in the classical sense. It can be many exotic things. So in particular, successful were what is called convolutional neural networks. So it's also, the method is almost 30 years old, first introduced by Jan LeCun in the end of the 80s. And this was the method that is currently among the best performing on some computer vision applications, and also the one that actually opened the gates of hell, so to say, in 2012, that basically introduced these methods in the computer vision community in a way that it was very prominent that's probably the right way to go. And if we compare the two different architectures, basically it's the same idea, but there are many differences between how convolutional neural networks looked in the 80s, in the 2010s. First of all, the networks are much deeper, many more parameters, about 60 times more parameters than before. The training set was significantly bigger and much richer. in terms of computational platform, it was based on GPU instead of a CPU, and also there are some architectural innovations such as the use of rails instead of sigmoid functions, and different types of regularization such as dropout. So I would say that the data was probably the key to the success of deep learning, and in fact there is maybe a little bit controversial statement that actually data is more important to breakthroughs in machine learning and artificial intelligence than the algorithms. And basically this table here summarizes the typical time that it took from the introduction of the algorithm to breakthrough versus from the publication of a data set on which the algorithm was trained to the breakthrough. And you can see the difference is pretty amazing. Average 18 years from the introduction of algorithm versus 3 years after the publication of the data set. And this is also probably true in case of computer vision. The ImageNet dataset was published in 2010, and the breakthrough happened in 2012. And when it comes to geometric data, to applications that this community is dealing with, actually, again, if you look at the history, if we go back maybe 20 years, there was just a handful of 3D objects that we could find. Well, I'm showing here the classical ones that you probably all know. If you look a decade back, there were some collections, but insignificant. We made our own collections, but overall we're talking about maybe at the best case a few thousands of shapes, like the Princeton collection here. But nowadays everything is different. There are huge collections of shapes, many commercial companies that are creating shapes, open source platforms where you can create, share shapes. Also, there was a quiet revolution in 3D sensing technology. So Kinect is probably the most well-known one. I was part of the team that developed the RealSense technology at Intel. So basically, and there are many other sensors. So you can actually, there are millions of these units sold. You can now have a 3D sensor on your laptop or tablet or even on your iPhone. Also, different efforts trying to collect biomedical data, such as the UK Biobank, which collects all kinds of data, including scans, MRI scans of humans. So basically, the different sources and different collections of 3D data are growing, which is extremely important for machine learning applications. So basically, we are talking, as I mentioned in the beginning, we are talking about geometric deep learning. This is a broader term referring to generalization of deep learning algorithms to non-Euclidean structured data. Mainly to graphs, I would say, in the machine learning community. So we've been working on graphs as well. I show here just a few examples of applications where ourselves and our colleagues have been applying these kind of new deep learning methods. For example, we worked on recommender system algorithms where you can incorporate social knowledge, or one recent paper that is now submitted for publication is neutrino detection in the IceCube telescope on the South Pole. These methods have been also used to detect particles in the Large Hadron Collider. We have a new startup company that uses these methods to detect fake news on social media, and so on and so forth. So I can continue this list, it will probably be very long. To our discussion today, there are also many applications in computer graphics and geometry processing. Obviously, virtual augmented reality, autonomous driving, robotics, medicine, even drug design. You can model protein interactions as geometric deep learning problems. We have a collaboration with people from Lausanne doing this kind of work. So I will start with a very brief introduction to machine learning, mainly focusing on convolutional neural networks. So it's just really very brief, the main notions, and then we'll talk about briefly about what we can call extrinsic or Euclidean type of methods, basically applying more or less traditional convolutional neural networks to geometric data in image-based or volumetric models. And then I will spend a little bit more time on point cloud applications, and most of the time on surface-based or intrinsic methods that are probably of the main interest to SGP community. And throughout, I will mention some applications and show different examples. Okay? So let's start with very basics of machine learning. So this is not supposed to be exhaustive. I'm talking about mainly supervised learning. So this is a toy example of supervised learning. We are given some data vectors, so think of images parsed into vectors. These vectors can be of very high dimension. If you think of even modestly sized images like 512 by 512, this gives us around 10 to the 5 dimensions. And basically in this very high dimensional space, we have data points, let's say, of cats and dogs, right? And we want to find a function that we denote by f that can tell us whether a given input is a cat or a dog image. Okay, very simple. So basically the function will be, in this case, will be a binary classifier. It will produce, let's say, +1 if it's a cat and -1 if it is a dog, right? So basically this transition, what is called the decision boundary, will look something like this, right? It will be some hypersurface in this high-dimensional space. So we are usually given a set of examples of inputs and desired outputs of the function. So it is sampled on a finite set that is called a training set, and we assume to be given a parametric model of the function. So we denote it by f subindex theta. Theta is a hypervector of parameters, which will be, for example, weights of a neural network. And the problem of learning or supervised learning is actually a problem of optimization, where we try to find optimal model parameters that minimize some loss function, basically some difference between the output of the function with given set of parameters from the given label, right, from yi. Okay, and basically different machine learning algorithms differ in the choice of the model, choice of the loss function, choice of the optimization procedure, right, and basically that's why there is a plethora of different choices, and this field is very rich and very broad. Okay, so the simplest example you can think of is a linear classifier. So basically our decision boundary in this case is just a hyperplane. We can write it, the equation of this plane, like this. And of course it not always works, right? Not always our data points will be linearly separable. So in many cases it will not work well, and it will produce some misclassifications. Okay, but let's stick to this example for a few seconds. So you can think of this, basically the way that it can be realized is in the form of the simplest neural network that is called historically perceptron. That was actually the first neural network introduced by neuroscientist Rosenblatt in the end of the 50s. And basically he actually described an algorithm that how to learn the weights of this neural network. What is used nowadays is different. Basically, the way that these neural networks are trained are by a procedure called backpropagation, which is just a fancy term for chain rule. Basically, you can, by knowing how the input is mapped to the output, you can reverse the computational graph and see how to update the weights. Basically, it's trained by gradient descent. Okay. So here maybe some technical thing. Usually there is a bias term which it is common to absorb into the weight vector. So from now on I will assume that it is part of the weight vector, right? And you can write this classifier like this. So basically we have a linear part and non-linear part that is called an activation function that basically maps, saturates everything at +1 or -1 in this example. Okay, now this is a very simple network. Actually, many examples are not linearly separable, and this was actually one of the main criticisms for perceptron. So people come up with more complicated networks where you can combine multiple perceptrons into a multi-layer network. So here you can see that each of these units is a perceptron that takes input and produces an output, and you can stack many layers of these perceptrons, and basically you get a multi-layer or a deep neural network. Okay, and basically the parameters of the network will be the weights of all the perceptrons together. So what can be said about neural networks? So it is quite an optimistic result if you consider even a very simple neural network with just 2 layers. So this first layer is usually called the hidden layer. Basically the set of the functions that these neural networks express is dense in the space of continuous functions. In other words, you can approximate any continuous function to any desired accuracy, right? And basically the statement is that there exists a number of neurons here and a set of weights W and A such that you can approximate any given function to any given accuracy. The way to think of it, the last layer is basically, as we've seen, is a linear classifier. So the hidden layer actually produces a non-linear coordinate transformation that warps all the data in a way that will become linearly separable. Okay, you can see it here. Now, so this is a good piece of news, but this result is more or less useless because it's not constructive. It doesn't tell us how many neurons we need, right? So it's an existence theorem. It doesn't provide any further information. it doesn't tell how to find parameters, how to avoid overfitting, or how well the network that we train generalizes to previously unseen examples. And in practice, it appears that if you try to apply such models to images, it will not work. Basically, the data is extremely high dimensional, so the number of parameters that you will get will be humongous. If you connect all the pixels and feed them into a neural network, you will get probably billions of parameters. Okay, so it doesn't work in practice. Actually, people in the past tried to apply these methods to images and didn't work. So what really worked was the realization that data is self-similar. So it has deeper statistical explanation of basically stationarity. I will not go into these details, but if you look at this example, at this image, so you see that if I want to make a classification, make a decision, for example, what kind of object is there. So this page and this page and this page, they all look the same. So I don't need separate weights for these pages, right? I can share the weights across the image. And this way save a lot of parameters by reusing the same weights. And this seems to be the way that our brain works. This is a famous result of Hubel and Wiesel, who got the Nobel Prize for this, research of the visual cortex of a cat. And basically, they found that there are locally connected cells that create deeper and deeper layers in the visual cortex. Some early versions of artificial neural networks that try to recreate this model are called neurocognitron. That's from the 1980. So this was inspiration for the modern version that is called convolutional neural networks. So another thing that we see also in the human brain is that basically as we go deeper into these neural networks, we start with very primitive features that combined together become more and more complex. So basically there is hierarchical or compositional structure. And if you see in this example, first we can detect edges, maybe some slightly more complex primitive structures like corners. And as we go deeper, we are able to detect entire objects, right? So there is even a joke among neuroscientists about the grandmother neuron. That's a hypothetical cell that will activate only when you see your grandmother. So probably it doesn't exist, but somehow it is close to it. So basically all these ideas finally come to realization in convolutional neural networks. So the way to think of convolutional neural network is think of the previous perceptron where you actually, instead of one-dimensional vector, we have a two-dimensional image. So basically the third dimension here are different coordinates that are called channels, right? And basically here we apply only local connectivity. So basically this can be thought of as a sliding window that passes over an image. Basically we can express it as in terms of convolution, and the coefficients of this filter are learnable. What is also typical in convolutional neural networks, well, at least depending on application, let's say application of image classification, is also to interleave convolutional layers with pooling. So pooling, basically, it's usually nonlinear reduction of the image size. So usually you aggregate locally the values of the pixels with some permutation invariant operations such as averaging or maximum. Okay. So typically the way it looks like, this is your input image, you apply filter. So this is the result of the convolution. Then you take, for example, blocks of 2 by 2 pixels, compute their maximum, and you get the result of the pooling, a smaller image that aggregates these outputs. Okay, so basically, if we look at the important properties of convolutional neural networks, obviously we get self-similarity and translational invariance. This comes from the translational invariance of convolution. We have compositionality because we use multiple layers. The filters are localized in space, right? So basically, one cell, if you wish, of a neural network doesn't know what happens very far away from it. In terms of computation, the number of parameters per filter is order of 1, right? So the filter is usually some block of pixels of fixed size, let's say 5 by 5. The complexity of applying a filter in each layer is order of n, right? So you just slide a window and you visit each pixel only once. And well, if you are talking about image classification tasks, usually the number of layers will depend logarithmically on the input size. So when we apply these kind of ideas to 3D data, there is actually a fundamental difference between images and geometric data. And what do you think is this difference? So the way we think of images is arrays of pixels. That's, I would say, 99.9% of applications use this representation. when we talk about geometric data, that's not such an obvious question, right? Depending on different applications, we might find totally different representations. And today I would like to talk briefly about different representations and focus mostly on this representation. So we can consider image-based representation, where we render our 3D objects from multiple views and then treat it as simply a collection of images. We can also rasterize the 3D structure and consider it as a volume, basically a collection of voxels. So instead of two-dimensional matrix, we have a three-dimensional array. We can also think of point clouds, so probably the coarsest, the most primitive, and the most basic representation of 3D objects, or surface-based, and that's actually probably something that is music to the ears of the SGP community. Basically, we like representing shapes as manifolds, as surfaces, and we'll try to generalize deep learning methods to these kind of structures. Okay, so I will start with image-based representation. So this is a work from 2015 by Kologerakis and co-authors. Basically, the idea here is very simple. Given a 3D object, we create artificial views, basically by simulating the way that a camera will see this object. So these are the 2D rendered images. And then we apply a standard convolutional neural network, the one that is used for two-dimensional images. On each of these views, each of these neural networks that is denoted here by CNN1 has the same parameters. So basically, it's a shared CNN that is applied to all the images together, and then there is a view pooling, so it's a max pooling that is applied across the corresponding pixels of different views. So we end up, after this max pooling, with a single image that somehow aggregates information from all the views. Then there is another neural network that is applied to this image. Okay, and finally we have an output that predicts the label of this object. Okay, so very simple. And in fact, one of the positive things that you can reuse as is, almost as a black box, some implementation of neural networks that are used in computer vision. It also produces reasonably good results, at least on applications such as shape classification. Now, on the downsides, the rendering itself might be slow and memory demanding. It is definitely not the right way of treating geometry. And also, what is important, there is no built-in invariance. So, for example, it will not work for deformable shapes. Or at least maybe I will take it in slightly more cautious way. Basically, you will need to learn invariance. So it's not built into the architecture. So if you want to learn invariance, you will need to show to the network a lot of examples, and probably the complexity of the network will be very high. So to give you an example, when such methods are view-based methods are applied to deformable shapes, such as correspondence between humans in different poses, work of Hao Li from 2016. They used the network with 200 million parameters, trained on 50 million examples for 2 weeks. So this is quite a piece of a neural network, pretty complicated. Okay, so this is definitely a big disadvantage of these approaches. Now, another approach still remaining in the with Euclidean representation, we can consider 3D shapes as volumes, right? So basically, we can generalize two-dimensional convolutional filters to three-dimensional convolutional filters. Same idea. So here you can see an example. So this is work from the Princeton group from 2015, where they did this model for the first time. There was parallel work from Maturana and Scherer from the same year, where they did more or less the same thing. So you can also see here that the size of the grid is very small. They applied it to cubes of size 32 cube, maybe slightly bigger. Nowadays you can find slightly bigger grids, but overall this representation is extremely coarse, and it is very expensive to use convolutions in 3D. Also, it's very wasteful representation, because basically you waste a lot of empty space. Where there is no object, you still have zeros, right? So you have a big array that contains zeros, but these zeros are wasted. And these methods actually work quite well. With all their disadvantages, you can find some impressive work. So I will show this result from recent work of from the group of Matthias Niester. They do scan completion and semantic segmentation. So pretty impressive results. So to address to some extent the computational complexity, several groups came up with proposals of using space partitioning methods, basically hierarchical volumetric representations such as KD trees or OC trees. And here you can see an example of how such a decomposition will look like. So you can go to higher resolution voxels. And you can also combine view-based and 3D-based representation. So this is another work from Nisser. So to summarize, basically here as well, you can use standard components, more or less. 3D convolutions are roughly like 2D convolutions. It also produces good results. Now, hierarchical methods, if you use them, they're not exactly standard, so you need some specially architected layers. In general, volumetric representation is wasteful. Basically, all empty space is just a lot of zeros that are not used. Complexity is usually high. The representation is usually coarse, so you can lose details or lose information in your objects. And again, there is no built-in variance, actually not even invariance to rotations. So if you rotate your object, the representation will change, and the response of the filters that you learned will also change. So again, you need significant amounts of data and complex and deep neural networks. Okay. So point clouds. Point clouds are probably the most primitive and the most basic representation of geometry. They are quite popular in some applications. So, for example, LiDAR-based acquisition of geometry, so something that is used in self-driving cars, for example. Typically, the output that you get from a LiDAR is something like this. So it's a point cloud. So when I say point cloud, doesn't necessarily need to be just X, Y, Z. It could also contain some extra information, such as color, may contain also information about normals, and so on and so forth, right? But for simplicity, let's assume that it's just X, Y, Z. So basically, learning on point clouds, one important thing to understand that when I give you a point cloud, basically there is no canonical ordering of the points in this point cloud, right? So any function that we learn on a point cloud must be permutation invariant, right? So here you can see I can order the points in the point cloud in arbitrary way, right? So here pi denotes some permutation of the indices of the points. Okay, and x here denotes some d-dimensional feature vector, which in the simplest case is just x, y, z coordinates. Okay, so basically deep learning on sets was explored in machine learning community in some recent works, but the first application of these ideas to geometric data is due to the Stanford group, Leo Gibbous and collaborators. And basically the idea is the following, that they apply a function that is shared in the same when applied to each point in the point cloud. So basically it's a geometric transformation that maps you from the, let's say, original XYZ coordinates to some higher dimensional feature space coordinates. Okay? And basically these, so this is denoted here. Usually it's implemented as a neural network. MLP stands for multi-layer perceptron. So it's a small neural network with a few layers that, let's say, maps from 3 dimensions to 64 dimension. Again, important, I would emphasize, the same function is applied to each point. Okay, and then if you want to, for example, to do shape classification, you also aggregate all the features on the point cloud by some permutation invariant aggregation operations such as maximum or sum. Okay. So of course there are many tricks that make this work in practice. One of important tricks is to use what is called spatial transformer units. So you can see it here. Basically there is a block in this neural network here that takes your input, which is a point cloud where each point is 3-dimensional, and transforms it by applying an orthogonal matrix, basically a geometric transformation, for example, to align the point cloud in certain canonical pose. Okay, and you can apply it also in higher dimension, where it's hard to interpret exactly what it does. For example, what is an orthogonal transformation in 64 dimensions? It doesn't have this immediate geometric interpretation, but this is what is essential for making this thing work. There are also many follow-up works. So this is a class of architectures that are called PointNet. There is a follow-up work that is called PointNet++ that tries to basically to apply PointNet hierarchically. Also a recent work, PCPNet from the group of Neil and Mitra that does a similar thing. And actually these architectures were quite successfully applied to different types of applications, such as object recognition, part or semantic segmentation, computation of local properties such as curvature or normals, or even some generative models that actually can, for example, take as input an image and generate a point cloud that basically reconstructs the 3D structure of this object. Okay, so what is remarkable, though, remarkably disappointing, I would say, in point nets is that it doesn't account at all for local geometric structure of the object, right? So we'll talk in a few minutes about surface-based representations, where this is actually given for granted by virtue of the representation. But in point clouds, you could in principle see that when you see a point cloud, that there is some local structure, it's just totally ignored. Basically what this function h learns essentially is some kind of space partitioning that will tell you, for example, how to distinguish a chair between a chair and a table. Okay, so halfway between point cloud-based representation and surface-based representation are graph-based representation. So you can think of the most trivial and straightforward representation of a local structure is by local neighborhood graph, k-nearest neighbor graph, or some epsilon ball graph that you connect a vertex I to, let's say, k-nearest neighbors j, right? And basically now you can apply neural networks that have been developed for graphs. So here I describe a particular architecture that we call edge convolution that we developed with the group of Justin Solomon at MIT. So basically the idea is the following. When you have a graph, let's think of this kind of graph. Basically there are two kinds of operations you can do. So you can collect information from your neighbors and you can aggregate this information, right? So basically these are the two basic things you can do on a graph. It's local processing, right? So basically the way of collecting this information is captured by what we call edge feature function. So basically each edge feature function takes the features from vertex I and vertex j, right? For each of the neighbors of vertex I. Okay, so it's a parametric function that again is usually implemented as a neural network. And the aggregation operation is something that is permutation invariant. So what is important that the structure of the neighborhood also doesn't have any canonical ordering. So we can number the vertices in the neighborhood in an arbitrary way, right? So in general, it will be something similar to maximum or average, right? So, but this is local aggregation. It's not a global one. We can also apply a global one, like in PointNet. Okay, so then we can define the operation that we call edge convolution. So we apply the edge feature function that takes as input the feature vector of the node itself and of its neighbors. And we do it for all the neighbors, right, for all the edges in this graph. And then we aggregate them using the local aggregation operation. Okay, and this produces a new feature vector that can actually be of a different dimension. Okay, than the input. So that's all. Here, basically the way that this function architected is also a big and open question. So we use, for example, a particular structure that took as input xi and xj minus xi. So basically, if you think of it, it takes the global position of the point and also the local structure of the neighborhood. So it actually benefits from both local intrinsic style type of operation and global point net style type of operations. If you have some additional information, for example, direction of normals at each point, you can, for example, compute a transformation, the way that a normal rotates when going from point I to point j. And this way, for example, this is a way of capturing curvature properties. Okay, so basically, bottom line, we have here a learnable local nonlinear operator that acts on point clouds. And we can actually see that many existing methods for learning on point clouds, on graphs, or on surfaces can be considered as particular cases of this architecture. So it's really very broad. So for example, many methods for deep learning on graphs that are based on Laplacian, applying Laplacian or some operations involving the Laplacian, as we'll see in a few minutes, are actually a particular case of this edge feature function that takes weighted difference between the feature at the point and its neighbor. PointNet and PointNet++ are just applying some feature function to the point itself and not considering any neighborhood, and some other architectures as well that we'll see in the following can also be cast as particular settings. So this is a very broad class of neural networks. What is important that the graph itself, basically the graph is constructed in the feature space. So for simplicity, think that this is a k-nearest neighbor graph. It actually doesn't make sense to always keep a fixed graph as deep learning on graphs does. We can actually update this graph after each layer. And the reason for this is that the structure of the feature space changes. And let me show you an example. So here is what I visualize is the feature space, the geometry of feature space of this point net type architecture at different layers of the network. And the task that we consider here is part segmentation. So basically, this is the typical output that the network will produce, right? And basically, of course, it's hard to visualize the geometry of high-dimensional space. So what I show is the distance in the feature space from red point on the point cloud, okay, measured in that particular feature space. So this is input. Here, the feature space is just three-dimensional Euclidean space. So the distance is Euclidean ball, right? Blue colors represent more distant points. And this, you can see that as we go deeper and deeper into the network, the distances become less and less geometric and more semantic. So you see that, for example, here we can, the points on the two engines of the airplane are close to each other. Or, for example, here, points on two wings are close to each other and the body of the plane is considered far away, right? And that's why it's important to update the graph between these layers. So just some results, how it works. So if we compare it to other point cloud models, deep learning on point clouds, this is currently state of the art, probably not for long, maybe already there are better methods, at least by the moment of publication it was the best. Here are some examples of segmentation of shapes. You can see comparison to point net. Well, these are probably examples that are selected to emphasize the advantages. Point net in general works pretty well, but you can see here some mistakes that it makes as opposed to this method that performs better due to its ability to capture the local structure of the neighborhood. So here are some examples of real-life scans. Again, you can compare it to PointNet. It produces less errors, especially in regions where it's not obvious how to segment. And here are some numbers that show that, again, currently it is state of the art. We can also compute local properties such as curvature or normals. And this is what I had to say about point clouds. So let's, in remaining time, talk about surface-based methods, right? And basically the main advantage why we want to talk about surface is dealing with deformable shapes. So I think this picture illustrates better than any words what exactly we are trying to do. So if you consider extrinsic representation, in this example it's view-based, right? So basically I apply a filter on an image that is seen by a camera, right? So the camera plane will be somewhere here. You see that when the surface deforms, the result of the filter will be very different, right? So the filter doesn't follow the surface. If I deform the surface, the result will be different. And as a result, I will need to apply a lot of different filters that somehow account for these deformations. So I will need to learn deformation invariance from many examples and basically pay for this invariance with huge complexity of the neural network. As opposed to intrinsic methods where I actually want to design this filter on the surface itself. So basically, this way, by construction, the filter is deformation invariant. As a result, I can dramatically reduce the complexity of the network and the number of examples, right? Because I don't need to learn the invariance, it is already built into the architecture. And I think it, philosophically at least, somehow it tells us that we don't need to apply deep learning as a black box. This is a powerful tool, and depending on the application, you actually have a lot of prior information, a lot of prior knowledge, a lot of good models about your data and about your problems. So in geometry, we have a lot of beautiful models that somehow risk to be thrown away by deep learning methods that are applied as black boxes. So I'm advocating for modeling as much as you can and learning everything that is hard to be modeled. Okay, and that's exactly the philosophy that we're trying to follow here. So basically, talking about non-Euclidean CNNs, we can also distinguish between different methods. Methods that work in the spectral domain, methods that work in the spatial domain, and we can also talk about methods that work in the parametric domain, and Keenan mentioned some of these methods yesterday, so I will probably not have time even to talk about it. So let's start with spectral convolutional neural networks. We'll see that this is one natural way of generalizing these architectures. Also, it has some problems. Okay, so just very briefly about our model, and again, I need to thank Keenan for giving a very good tutorial about conformal geometry where he covered also basic notions and Riemannian geometry, so I will just mention it very briefly. So we model shapes as manifolds, basically two-dimensional boundary surface of 3D objects. We cannot think of them globally as Euclidean space. You can think of them locally. Basically, you have some Euclidean structure that is attached to each point, basically what is called the tangent plane. And on this tangent plane, we can define an inner product that is called the Riemannian metric. And quantities that are expressed in terms of the Riemannian metric are called intrinsic, and isometries are deformations or transformations of the surface that do not change the metric. Okay, so if you think of a piece of paper, if you bend it without stretching or tearing it, this is an isometry. Okay, now we're also interested in doing operations with functions on manifolds. So for simplicity, think of scalar functions or scalar fields. Now, unlike 2 points on a manifold that you cannot add or subtract, you can add or subtract functions on manifolds, right? So formally, we can talk about Hilbert space with, for example, this inner product that can be defined for the space of functions on manifolds. And an important operator that can act on these functions is the Laplacian operator, so I will not go into the details. It's the generalization of the classical Laplacian in the Euclidean space, so non-Euclidean space. In differential geometry, it's sometimes called the Laplace-Beltrami operator. So an intuitive way of thinking of the Laplacian is you take an average of your function in infinitesimal neighborhood of a point and subtract it from the value of the point itself. And when talking about infinitesimal neighborhood, of course, you need to account for the metric structure. So basically, the metric is hidden in the definition of the Laplacian. It is intrinsic, so you can express it entirely in terms of the Riemannian metric. As a result, it is automatically isometry invariant. Not only the Laplacian, all the derived properties. It is self-adjoint or symmetric, and as a result, it has orthogonal eigenfunctions. And it is positive semi-definite, therefore, it has non-negative eigenvalues, right? So we'll see in a second how we can use the eigenfunctions of the Laplacian as an analogy of Fourier basis in the classical analysis, okay? So obviously we're interested in practical applications to work with discrete structures, so there is a zillion of different discretizations of Laplacians. Here actually a word of warning. There is no free lunch theorem for discrete Laplacians or discretized Laplacians. You can actually not satisfy all the continuous properties of the Laplacian, and usually some of the discretizations lose some of the properties. So for example, you can lose positive semi-definiteness, or you can lose symmetry. So you should use wisely the discretization that you choose. And in particular here we are interested in discretization that is that, as I mentioned before, provides non-negative eigenvalues and is symmetric, so the eigenfunctions are orthogonal. So the Popper cotangent discretization actually satisfies these properties. Is, for example, we don't care about the maximum or minimum principle. Okay, so bottom line, you can discretize Laplacian as a big sparse matrix that acts on your functions on the manifold, or on the mesh in this case, that are represented as vectors. Okay, so sometimes in physics you call this W the stiffness matrix, and A is called the mass matrix. Okay, so here we'll assume that it's diagonal. Okay, now this is how the eigendecomposition of this Laplacian looks like. So it's symmetric matrix. You can think of it as a generalized eigendecomposition problem. So the eigenfunctions will be a set of, or eigenvectors will be an A orthonormal matrix. Okay, so somehow not to carry around this diagonal matrix A, you can always, by change of variables, make the eigenfunctions orthonormal, right? So from now on, I will assume that they are simply orthonormal. And basically, this A can be hidden inside the inner product if you wish. Okay, and you can actually see that if you take a Euclidean Laplacian, then its eigenfunctions are the classical sines and cosines, right? So basically, we get the standard Fourier basis as eigenfunctions of the Laplacian. On manifolds, this is how eigenfunctions of the Laplacian look like. So basically, this is a generalization of the Fourier basis, right? And a reminder, in classical analysis, you can take a function and express it as Fourier series, right? So basically, what is written here, this is a projection of my function onto the basis of sines or cosines or complex exponentials, right? So these are called Fourier coefficients or Fourier transform. And this is sum of these coefficients multiplying the basis functions, right? So basically, what is written here is just the fact that you can take a function and represent it as sum of sinusoids of different frequencies, right? With coefficients that are called the Fourier coefficients. So the fact that the analysis and the synthesis is done in the same basis is due to the basis orthogonality, right? And as I said before, these sines or cosines are the eigenvectors of the simple Euclidean Laplacian. So you can do exactly the same thing on manifolds, where you just replace the sines and cosines by the eigenfunctions of the Laplacian, right? In this case, the Laplace-Beltrami operator. And that's why you can interpret eigenvalues as frequencies and eigenvectors as Fourier bases, right? So another important construction in classical analysis is convolution. So this is an integral operator that is given in this form. And basically one of the important properties is that it commutes with the shift operator or shift invariant. Basically meaning that if I first apply shift and then do convolution, or if I first do convolution then apply shift, I will get exactly the same result. Also, what is important that convolution commutes with derivative, with the Laplacian, and basically two commuting operators are jointly diagonalizable, meaning that the convolution operation, basically this operator has the same eigenbasis as the Laplacian, right? In signal processing, sometimes this is called the convolution theorem, basically saying that Fourier transform diagonalizes the convolution operation, and as a result we can implement convolution in the Fourier domain simply as element-wise product, right? So if you think of it, this is bread and butter of signal processing, because we have an efficient algorithm of computing Fourier transform using f of t, and usually the filter, so if you think of f as a signal and g as a filter, the filter is designed already in the spectral domain as spectral response function. You apply f of t to compute the Fourier transform of your signal. You apply the filter by element-wise multiplication, so costs you order of n, and then compute inverse Fourier transform. So overall you pay n log n complexity, right? So this is basically, you find this thing everywhere, from your cellular phone to your stereo system, right? So this is classical signal processing from the moment the fast Fourier transform was invented or reinvented in the 70s. This is how it is done, okay? Now, if you write it in the discrete setting, just to see it in a slightly different way, so this is the integral operator that we've seen before, now represented as a matrix. This is our signal, and this matrix is a very special matrix. It is what is called Toplitz or circulant matrix. Basically, each subsequent row of this matrix is a cyclically shifted version of the previous one, right? And these matrices are known to be diagonalized by the Fourier basis. So basically, in the Fourier basis, we can write it like this. So it will be a diagonal matrix containing the Fourier transform of the filter coefficients G. And this is the forward Fourier transform, this is the inverse Fourier transform, right? So forward Fourier transform, let's write it like this, as f hat, right? So here we have a diagonal matrix multiplying a vector, which is nothing else but pointwise multiplication, right? So this is a matrix version of the convolution theorem. Okay, so we can replicate the same thing on general domains, on manifolds. So we can define a kind of convolution that we call spectral convolution by analogy. So something that is a property in the classical setting can be used as a definition in the non-Euclidean setting. So we can define spectral convolution as computing Fourier transforms of f and g, right? Basically projecting them on the Laplacian eigenvectors, and then computing the inverse Fourier transform, right? Using these coefficients, multiplying them by the basis function and summing everything up, okay? So this is product in the Fourier domain, and this is the inverse Fourier transform. Now, in matrix vector notation, we can write it like this. Fourier transform of f, Fourier transform of g, element-wise product, inverse Fourier transform, okay? Or, basically, this is a matrix that we denoted before by g. So now, this g is not shift invariant anymore. It doesn't have this circulant structure. And what is more important, that these filter coefficients will depend on the basis phi, right? So before, in classical setting, the space is fixed. So I give you a space, basically, this is some regular grid. These phis are sines or cosines, right? Here, each shape will come with its own set of Laplacian eigenvectors, right? So basically, it will not be easy to adapt the filter from one shape to another, okay? So basically, this is what all we need to know to do spectral CNNs. And in fact, this was the construction proposed by Joan Bruna and co-authors in 2014. They applied it to graphs, but the ideas apply exactly in the same way to manifolds. Basically, you implement convolution in the spectral domain. You compute Fourier transform of f, right, by projecting on the Laplacian eigenbasis, multiply by diagonal matrix of learnable filter coefficients, and compute the inverse Fourier transform by multiplying by phi. Right? That's all. Now, what is important, as I mentioned, filters are basis dependent, so it's not easy to make them generalize across different domains. I will show an example in a second. The number of parameters per layer is order of n. This is the size of this matrix W, as opposed to order of 1 in the classical CNNs. Also, the cost of the computation, you need to multiply by a dense matrix phi, right? I'm even not talking about computing the eigenvectors, which usually costs roughly order of n cube. So, assuming that these vectors are pre-computed, you usually don't have f of t on graphs or manifolds. So this is multiplication by a dense matrix. Okay? And also the filters are not guaranteed to be spatially localized. Okay, so we'll try to solve these problems one after another. Okay, let's first talk about the basis dependence. So this is actually a crucial thing to understand. So let me show you an example. So this is a manifold, and I have some function on this manifold. Okay, so the function is 0 at the gray regions and 1 at the red regions. So some kind of blobs. Okay, and this is a filter I apply to this function. I apply it in the spectral domain. So I first compute the Fourier transform, then multiply by diagonal matrix of spectral coefficients, compute the inverse Fourier transform. Okay, and this filter does some kind of edge detection. So it goes from these blobs to these blobs. Okay. Now, if I slightly deform the shape, keeping the same filter coefficients, but now using the basis of the corresponding shape, what do you think the result will be? Completely different, right? Completely different. So basically, the filter coefficients do not speak in the same language. They were derived assuming some basis, and now the basis has changed. And you can see this is especially prominent in high frequencies. So this is how the 50th Laplacian eigenvector looks at this course. So you see that it changes a lot, even across almost isometric deformations of the surface. Okay. Now, and this is another example. So you can see that maybe, well, of course, there is first of all some ambiguity in the definition of the eigenvectors that is sign or maybe rotations in the eigen subspace if you have multiplicity of the eigenvector. But in general, this discrepancy between different eigenfunctions increases with increasing frequency, right? So you see that the eigenvectors of the Laplacian are different. So a way of synchronizing the basis, basically we want our Fourier coefficients to talk in the same language, right? So we want somehow to synchronize the basis. A way of thinking of it is in terms of functional maps. So I don't know how many of you are familiar with functional maps. We'll have a session tomorrow with several works on this topic, but so this is a concept introduced by Max Ovsyannikov and co-authors in 2012, and the idea is the following. If you have two functions, one function f that lives on the first manifold and function g that lives on another manifold, you can express the correspondence between functions, these functions as a linear operator between the respective functional spaces, right? Now, each of these functions can be expressed in the orthogonal Fourier basis, in the Laplacian eigenbasis on each of the shapes. So I denote the decomposition coefficients by f hat and g hat, okay? Now, you see that these coefficients usually will not be the same. And basically, this correspondence between coefficients can be encoded by a matrix. That if the basis is truncated to the first k coefficients, will be k by k. And usually the matrix looks like this, right? So basically, what this matrix C does, essentially, is a low-rank approximation of the correspondence operator T. So if I write everything as matrices, I will first do Fourier transform on the first shape, right? I will then transfer the Fourier coefficients to the other basis on the other shape and do the synthesis on the second shape, right? Now, if you think of this C transpose phi transpose as a modified version of phi, right? So basically a transformed version of phi, let's call it phi bar. Now, this phi bar will be a synchronized basis to the first one. So in this new basis, psi and phi bar, the correspondence matrix will be identity, right? So in other words, the Fourier coefficients speak in the same language in these two bases, okay? And now basically what we want to do is we want to apply our filters, our spectral filters, in consistent, in synchronized basis, right? So if you look at this example, so this is how my spectral filter looks like. I apply to a delta function at corresponding points on these two human shapes, you see that the result is different, right? But if I choose some canonical shape with some basis denoted by sigma and eigenvalues lambda, if I apply the filter by first going to the canonical basis, applying the filter there and then going back, I will get the same result, right? So I always use the same basis in which I apply the filter. Okay, so this is the idea of spectrally synchronized CNNs or spectral transformer networks. And basically, if you compare it to the simple spectral CNN, it has this additional component that finds the matrix C, that first applies it before applying the Fourier transform, right? So basically, it modifies the Fourier transform and then modifies the inverse Fourier transform. Okay, so this is similar to the idea of spatial transformer networks that is used in computer vision, where you basically create a kind of canonical alignment of your input image. So here the canonical alignment is done in k-dimensional space of eigenvectors. Okay, so what is good that it solves this problem of generalization across different domains. Unfortunately, it still requires to apply the Fourier transform, which is expensive, and it's, at least I don't see a simple way around it. Okay, and here are some results. So this is also work from the group of Leo Gibas. They show that actually it works pretty nicely, at least on some rigid objects such as chairs or tables and lamps, the usual computer graphics objects that you will see. Okay, so back to spectral CNNs. Another problem that we've seen before is lack of localization, right? So if I give you, basically if I parameterize the filters in the Fourier domain, nothing in the world guarantees that the resulting spatial version of the filters will be localized, right? And in the classical case, we have this property of the Fourier transform that relates higher-order derivatives of the Fourier transform to the higher-order moments of the function in the spatial domain. And basically, if we want the function to be localized in the spatial domain, we want the higher-order moments to vanish, meaning that the higher-order derivatives of the Fourier transform must vanish as well, meaning that localization implies smoothness in the frequency domain, right? And basically, what we can do is to parameterize the filter using a smooth spectral transfer function. We denote it by tau of lambda. And basically, we apply it to the Laplacian in the operator sense, meaning, of course, not applying it element-wise to the Laplacian matrix, but applying it to the Laplacian eigenvalues, right? Because this is a diagonal matrix, we can apply tau to each of the eigenvalues, right? And basically, by parameterizing this function with a small number of parameters, we can just learn these parameters. Okay, let me show you first an example how this looks like. So this is a non-smooth filter. You see that it has a lot of oscillations in frequency, and you see that it's not localized, right? So I'm applying it to a delta function at the white point, and you see how it looks like. So it has global support on the shape. You can also see that it's not very stable, as opposed to a smooth filter that is localized and much more stable. So in general, spectral filters that are stable somehow need to decay fast and be smooth in the frequency domain. So look something like heat kernels, more or less. Okay, so one of the simplest ideas, one of the simplest choices of this spectral transfer function is a polynomial, which is smooth by definition, right? And basically, what is important about polynomials is that you can apply them. First of all, the number of parameters in this case of the filter is order of 1, right? So this is the number of coefficients of the polynomial here. What is important that you don't need to explicitly compute eigendecomposition of the Laplacian, because you can actually compute the polynomial by just applying powers of the Laplacian, right? So this particular filter doesn't require explicit eigendecomposition, so you can just pay order of n complexity instead of order of n squared. Right? Because Laplacian is a sparse matrix, its multiplication by a vector costs you order of n operation, so you do it r times, take r's power of the Laplacian. Okay? What is important that because Laplacian is a local operator, so on the mesh it touches only your direct neighbors, what is called one ring. So the r's power will touch only the r ring, right? What is of course a disadvantage that it is mesh dependent in this formulation. Basically, if I look at a filter on a very dense mesh, it will have very small support. On a coarser mesh, it will have a bigger support, right? So it is better to use functions of the Laplacian that also include Laplacian inverses, basically rational functions, and you know that you can express many filters, like heat kernels, for example, on meshes using rational functions such as Padej-Chebyshev. In this case, we use Cayley polynomials. So this is work that was applied on graphs, but we can do the same thing on meshes. Basically, we have a rational function that includes both powers of the Laplacian and inverses of the Laplacian. So in this case, it's a complex function, but doesn't really matter, right? And basically here we have again order of 1 parameters per layer. We don't have compact support anymore for the filters, but we can show that in some sense they decay exponentially. Basically, if you think in terms of signal processing, the difference between the polynomials and rational functions is like finite impulse response and infinite impulse response filters. And the infinite impulse response filters, you have fixed number of coefficients, but the support can be global. Okay. Now, the caveat here is that inversion of the Laplacian in general is a computationally intensive operation, order of n cube. But if you can approximate this inversion using a fixed number of, for example, Jacobi iterations, you bring it back to order of n, because you just need to do a fixed number of multiplication by the Laplacian. Okay, and basically it's a richer class of filters compared to polynomials, so usually it produces better results. Okay, so let me show how it looks like. Yeah.
Is it not easy to invert it once we have already computed the eigenfunctions?
Well, so first of all, computing the so the question is, if we already computed the eigenfunctions, does it help the inversion? So usually computing the eigenfunctions costs you also order of n cube. So you don't save anything, right?
So in all your work, you are trying to avoid computing them.
So here you try to avoid computing them because you because even if you have computed them, multiplying by them costs you order of n squared. Here we want complexity of order of n, linear complexity in the input. Yeah.
Okay.
So this is a sanity check. So always when trying to generalize, it's good to go back to the trivial example, in this case, the Euclidean grid, two-dimensional grid, and see how such filters look like. So this is an example of polynomial filter of order 3 that is applied to a delta function at the center of this grid, and you can see that the support is exactly 3 pixels removed. This is how it looks in the spectral domain. So it's a very smooth function, right? So this is polynomial of higher order, r equal to 7. So we have bigger support for the filters and slightly less smooth function. This is what you get with rational functions, with Cayley polynomials. So you can see that the support can be either large or small with the same class of filters. And this is how the spectral transfer function looks like. Now, what is also striking here, and this is not surprising at all, in the Euclidean case, the Laplacian is rotation invariant. So I don't. Somebody wants to talk. So the Euclidean Laplacian is rotation invariant. So I don't know if you know how to prove it actually, because usually when you write the Laplacian, Euclidean Laplacian, it's sum of the second order derivative with respect to x and with respect to y, right? So basically the trick, if you want to prove it, is to write it as a trace of the Hessian matrix, and then use the chain rule when you apply orthogonal transformation. Then matrices commute under trace and rotations cancel out. Right? So geometrically, as we've seen, Laplacian it can be interpreted as local averaging in a small neighborhood minus the value of the point itself. So that's why it's actually easy to see from that definition that it should be rotation invariant. And indeed, the filters that we get here are rotation invariant. So this is a kind of boring filters. If you try to apply such filters to images, probably you will not get too far away, right? So we'll see actually we'll see in a few minutes how to design anisotropic Laplacians. So these can be, basically these filters can be made directional. Okay, so let's talk about spatial domain methods. How am I doing with time? 25 minutes, including questions. Oh, okay. Yeah, I think I'm good. Okay, so spatial domain. Basically, what we've seen, if we look at the definition of convolution, right? So that's the main ingredient of convolutional neural networks. We want to generalize. We had two definitions in the Euclidean domain. We had the definition of the using an integral, or definition using the Fourier transform, right? So we've seen that it's straightforward to generalize the Fourier transform, just replacing Fourier transform with projection on the Laplacian eigenfunctions. The question is, what would be the spatial analogy of convolution on meshes, right? So an easy way of thinking of convolution is a kind of template matching, right? So you pass a mask on your image, and you basically you extract a patch of pixels, you multiply it by the mask, you sum everything up, and you get the result of convolution, right? Or correlation. That for the purpose of this discussion is the same. When you move to a different pixel, the very operator that extracts this patch of pixels is exactly the same, right? So it's a shift invariant operation. When talking about non-Euclidean spaces, graphs, or manifolds, that's not the case anymore. Basically, when I move from point X to point X prime, the extraction of the pixels should change. If I consider a certain patch around the point, even the number of points in that patch might be different, right? Or on general graph, the connectivity can be completely different. The valence of a vertex can be very different, right? So basically, the way to do it with it, so on graphs, there are different ways of doing it. For meshes, we actually have the luxury that we have some clearly defined local structure. Basically, we can come up with a local system of coordinates. I denote them by U. Subindex ij tells you that basically this is a system of coordinates constructed around point I, and this is the coordinated point j, right? So, for example, we can think of geodesic polar coordinates. So the first component will be the geodesic distance, and the second component will be some notion of angle around a point. Okay, and in this system of coordinates, we apply a set of local weights, overall L weights, that, for example, look like this, right? So here you can see the geodesic coordinates, and these are the level sets of these weighting functions. Okay, for example, these can be Gaussians. Okay, so think of these weights as pixels. Basically, we don't have now a fixed set of pixels. It would be wrong to think of vertices as our pixels in the basically in the analogy to patches and images. Now think of these weights as pixels. So we do local averaging of our function on the manifold, and each of these averages corresponds to a pixel. So basically, we call this the patch operator. So it is always L-dimensional at each point, and then we apply to it this mask G. These are the filter coefficients, and sum everything up. Okay, I write here not equality but proportional because I'm lazy to write normalization by the sum of all the filters. Right, I just don't want to carry this denominator around, so it is somewhere hidden here. Okay. Now geodesic polar coordinates look like this. So here we have the radial coordinate. Here we have the angular coordinate. And basically one thing that is obviously you can observe is that usually there will be some orientation ambiguity. Basically how to choose the origin of the angular axis theta equals to 0, right? So there are several ways of dealing with it. First of all, you can establish some canonical direction. This can be, for example, some vector field that you can define in a repeatable way on the manifold. It can be, for example, a gradient of the geodesic distance, or not exactly intrinsic. You can use the maximum curvature direction. Then you can basically look at all the possible rotations and choose the one that responds the best. So basically apply a kind of rotating mask and take the maximum. So this is what we call angular max pooling. Or you can do the Fourier transform magnitude trick, and basically the idea is that you apply standard Fourier transform with respect to the coordinate theta, and then rotation becomes a complex phase. If you take absolute value, you get rid of the phase. Basically, you get rotation invariance, right? Now, I will not go into the details. You basically more rigorous people in this audience may ask, what happens with the injectivity radius? Basically, if the distance, the geodesic distance is too large, then this is not a disk. We don't really care. So I will give two motivations why we don't care. So first of all, let's say we choose the patch sufficiently small. When still you have very large curvature, it might not be a disk. So in this case, probably the result that the neural network produces at these points will be garbage. So some points will be not meaningful. As I will try to convince you that that's not a problem. For example, for problems such as correspondence, we can easily cover up for these points. Also, the construction that I will show you slightly later, where we actually learn the weights of the patch operator, basically the learning process will automatically determine the correct scale of the patch to avoid such problems. Okay, so of course there are some technical issues that might come up here, but I think it's important to be aware of them, but not to be worried about them too much. Okay, so these are different constructions that we can, at least that we explored, how to construct these systems of weighting functions. So the first work actually that proposed a generalization of CNNs to meshes was what we call Geodesic CNN, published in 2015, that used actually a system of weights that we did in prehistoric work from 2012 that was used for intrinsic shape context on meshes. Okay, and basically here we have a fixed set of bins and Gaussian weights applied to each bin. And basically here we apply the page operator, we apply rotating filter, so we account for different possible rotations of the filter, and then take the maximum of the result. So this is the angular max pooling. And I will show you an example how this can be used for learning optimal local descriptors. So basically local descriptors, as you know, you can use them for many different applications, for shape correspondence, for shape recognition. Basically here we assume that we are given a training set of shapes with known pointwise correspondence. Could be dense or sparse. Here usually we use models such as Faust. And basically we have triplets of points. So we have a point xi, we have a corresponding point that I denote by xi plus, and a non-corresponding point that I denote by xi minus. Okay, and they are color coded here. So basically what I want on this training set is to train a neural network, right? So the neural network will be producing pointwise features here, right, by applying a few convolutional layers to the input data. And I want that for positive pairs, the output of the neural network will be as similar as possible. And for negative pairs, it should be as distant as possible. This plus denotes here hinge loss. Basically, it means that the 2 points should be, the 2 descriptors should be at least mu apart in the feature space. Okay, and basically in machine learning literature, this is typically referred to as Siamese architecture. You have 2 identical copies of a neural network with the same parameters. You feed it with pairs of points. It produces pair of descriptor, and you compare them. So the loss compares these pairs of descriptors. Okay, so this is, you can think of it as a metric learning. Okay, so here is some visualization of how these descriptors look like. So basically what I show here, again, it's hard to visualize high-dimensional descriptor space. So I show here distance from the descriptor at the white point to the descriptor at all the rest of the points on the same shape and on other shapes. Okay, and basically I use here a color map that cold colors represent small distances and hot colors represent large distances. Okay, so this is heat kernel signature, famous descriptor that is used in computer graphics, also due to Max Ovsyannikov and co-authors. And you see that it's very poorly localized. It is very smooth, which is not surprising. Basically, it's based on heat kernels that are smooth. This is wave kernel signature, a different model from the group of Daniel Kremers. And you see that it is much better localized, but much more spurious. So, for example, point on the shoulder for some reason looks like points on the belly of this shape. And this is what we get with Geodesic CNN. So you see that it's both more specific and better localized. And basically, if you do the standard quantitative comparison, CMC curve, ROC curve, first neighbor correspondence, it performs much better than the handcrafted descriptors. Okay, now I should say that this was 2015. We can do much better now with more clever architectures. Okay, but still the difference is pretty dramatic. Okay, so another way of computing these local weighting functions is using anisotropic diffusion. Okay, so let me just talk very briefly about diffusion. So this is a diffusion equation that we are all familiar with. So basically, it's a differential version of what is called in physics the Newton law of cooling. Basically, it tells you that the rate of change of temperature of a body will be proportional to the difference between its own temperature and the temperature of the environment. Okay, so the rate of change is the temporal derivative, right? F is the temperature, and the difference between the temperatures is encoded by the Laplacian operator here. Okay, so this is homogeneous diffusion where the thermal conductivity property of the surface are the same at each point, right? So that's why this is a constant that can be taken out of the divergence, and then divergence of the gradient is the Laplacian. So that's the familiar form of derivative of the temporal derivative of f equals to Laplacian or minus Laplacian of f, right? The diffusion equation. Now here we are interested in anisotropic diffusion, where actually diffusion properties or the conductivity properties are position dependent and direction dependent. And this can be modeled by this, what is called in physics anisotropic tensor. So this is a matrix that multiplies the gradient and it changes at each point. Okay? So to give you an example, the difference between isotropic diffusion and isotropic diffusion is here. You see that here heat goes uniformly in all directions, and here it has some preferred direction. Basically it goes faster in vertical direction. Of course, the term vertical here is totally inappropriate because it's all intrinsic. So basically there is some tangent vector field here that guides this diffusion, makes it faster along certain directions. Okay, so the way that some technical details how this is implemented. So basically you can introduce an isotropy into the Laplacian in the following form. You take the gradient, right, which is, I remind you, a tangent vector, right, at each point. You multiply it by rotation matrix with respect to some canonical system of coordinates. So we use principal curvature, which is a lazy choice. You can use something that is an intrinsic tangent vector field. You multiply it by a scaling matrix that creates the anisotropy, and you rotate back. Okay, so we call this an isotropic Laplacian, and it has these extra two parameters: the rotation and the anisotropy or elongation, right? And you can define heat kernels with respect to this Laplacian, similar to the standard ones. Basically, now we have three parameters. We have the scale, basically how much the diffusion is allowed to take, the orientation, and the anisotropy, right? So basically we get this family of blobs that can be oriented differently and can become thinner or thicker, and can have different sizes. Okay, and basically if you think of the representation of local system of coordinates, they look like this. Okay, so the final architecture I would like to show you is actually a better version of all the previous ones, where we don't assume that the weights are fixed, we allow them to learn. And again, we use, for example, geodesic polar coordinates. We assume that we have Gaussian weighting functions in the system of coordinates, and we assume that we can also learn the covariance and the mean vectors of these Gaussians. So basically we have this expression of the spatial convolution. We can also see that if you can exchange between the basically between the integration over the manifold and the summation over the different weighting functions, what is written here is a Gaussian mixture, right? So basically we are trying to find parameters of the Gaussian mixture that will produce an optimal patch, and that's why we call this mixture model networks, or MONET for short. Okay, and of course this generalizes the previous approaches, including classical CNNs, geodesic CNNs, and isotropic CNNs. So this is a richer family of filters, and this result is expected to work better. So I will show you how to apply it to the problem of finding correspondence between deformable shapes. So there are actually different ways of thinking of correspondence. You could, in principle, use the descriptors that optimal descriptors that we learned before to find correspondence. You can also consider correspondence in a different way, basically as a labeling problem. So let's say that you are given a class of shapes, let's say human shapes. Choose one of the shapes and consider it as a reference label space, right? So let's say that the query shape has n vertices and the reference shape has m vertices. So basically correspondence consists of labeling each point on the query shape with the corresponding point on the reference shape, right? So it's multi-class classification problem. The number of classes here is large. Typically we use shapes from Faust as reference, so it's around 7,000 classes. Okay, so basically the output of the network, we use as the final layer a softmax. Basically you can interpret it as the probability distribution of I corresponding to point j here on this shape, right? And basically we can use the standard classification loss cross entropy between the ground truth correspondence and the output probability that is produced by the network, right? So the way that we measure the quality of correspondence is also a standard thing. I think it's been used around, but probably formalized by the work of Kim and Kosres, Kim, Lippmann, Funkhauser in 2011, where they also published the famous Princeton benchmark. So basically we measure the geodesic distance on the target surface from the correspondence that I denote by pi I, that is produced by our network, to the ground truth correspondence that is denoted by pi star. Okay? And basically this gives us a pointwise error we can visualize it. We can see basically what's the distortion of the correspondence at each point, or we can just aggregate it and tell what is the average distortion or the maximum distortion on the of the shape. Okay, and the usual plot that is used to show the quality of the correspondence is to take basically some tolerance. Usually it's expressed in either in centimeters or in percent of geodesic diameter, and you see how many points fall within this geodesic distance tolerance, and you see some monotonically increasing curve. So this is the results that we obtain with different architectures. Just for reference, BEAM is the blended intrinsic map, the work of Lippmann and co-authors, that doesn't use any learning. So it is based on Möbius transformations, as Kinnan explained yesterday. The green curve is random forest. So this is work of Emanuele Rodola, one of the first works to do learning, not deep learning, but kind of machine learning for correspondence problems. And these are the different architectures that we've seen before, GCNN, ACNN, and Monet. So you see that with Monet, we got almost perfect correspondence. About 90% of corresponding points have zero distortion, and the maximum distortion is around 4%, so roughly the size of the finger. So maybe a good way to visualize it is by plotting the point-wise distortion, so the distance from the ground truth correspondence. So this is what you get with blended maps. It is actually hard to see it because usually blended map produces smooth correspondence, but it's a bad correspondence. This is what you get with Geodesic CNN. So you see few points where the distortion is large, but overall it is almost zero. ACNN produces better results and even better results with Monet. Okay, so a better way of visualizing it is by using texture mapping. So if I transfer texture from reference to the target, you can see that the distortions are minimum, maybe a few here in the non-isometric Pele area. You can also apply it to shapes with missing parts or different types of noise, for example, topological noise you can see here. And you can see that the distortion is pretty small. Again, if we visualize it with texture mapping, in this case it's just color coding the corresponding points, the results are pretty good. You can maybe find some artifacts here, but it's even hard to see. This is another example. Okay, so it works pretty well. Now, if we look at again at the problem of considering correspondence as a classification, one of the obvious disadvantages of this approach that it's not geometric, right? So classification tells us that we are good if we hit exactly the corresponding point. But if we are slightly away from the corresponding point, it will not tell the difference between being epsilon away or very much away, right? So basically from classification point of view, pi prime and pi are equally bad, right? Because they didn't fall on the ground truth correspondence exactly. So a better criterion for correspondence, this is something that we call soft correspondence error. Again, I think it's been used more or less by everyone, but probably we were the first to formalize it in our 2015 paper by Artem Kovnatsky. And basically what we do is the following thing. We assume that, remember this pi ij, so this is the probability distribution that is produced by a network, basically the probability of I corresponding to j. And basically we weight the geodesic distance by this probability distribution. So basically we account for all the possible points, but weight by their probability. So if we have a delta function at exactly the corresponding point, then basically this error will be 0. If we have something that is centered around the ground truth corresponding point, but is a narrow Gaussian, for example, then we'll get small distortion. If we are far away, then we'll get a big distortion. Okay. Another problem is that during the training, we can minimize this distortion, but nothing guarantees that at test time, two nearby points, I and I prime, will correspond to two nearby points on the target surface that I denote here by j and j prime. It is possible in theory that my correspondence algorithm will produce, will map I prime to j prime prime that is very far, right? So this is also a common problem in computer vision problems. For example, when you do semantic segmentation. So if I produce, for example, a pixel, I label a pixel as a human, it is very likely that nearby pixels will be human as well. So somehow the decision on one pixel conditions nearby pixels, right? So it's not an independent decision anymore. So we want somehow to introduce the fact that correspondence is not just a pointwise decision that it has some global structure, okay? And again, we'll use functional maps to do this structured prediction. And I remind you that functional maps consist of representing the correspondence, basically linear operator that maps functions from one manifold to another in the Fourier domain, right? So basically we map Fourier coefficients of the decomposition of f and g by a matrix C. Okay, so basically if you're given some set of descriptors, I denote them by f1 through fq and the corresponding ones by g1 through gq. Basically I have a system of equations that are related by this matrix C, right? And basically you can recover C by solving this system of equations in the least square sense. Okay, basically you have a closed form solution for this system of equations. So basically if you look at this C again in the spatial domain, so this is a low rank approximation of the correspondence operator. Basically, if we normalize everything appropriately, you can think of it as a probability of mapping one point to another point, right? So basically, the functional correspondence, after we use a truncated basis of the green point, will look like this. Now, it's important to take absolute value and normalize because it might have also negative values, right? But basically, after normalization, we can think of it as probability. Okay? Now, this was our descriptor learning, right? And this descriptor learning considered pointwise descriptors. So in this procedure, I didn't care about other points. So basically what was important that each point that is corresponding to another point is mapped to nearby points in the descriptor space. And if the points are not corresponding, they are mapped far away, right? So here we are now doing a different process. We want to design descriptors that when used with functional maps will produce the best results. And in the sense that the soft correspondence that will be produced will be minimized, the soft correspondence error, right? So the way it works, the neural network produces pointwise features. Then we apply the Fourier transform, right? So we produce Fourier transform of these features. Then we apply functional maps to compute the matrix C, and this matrix C is used to compute the spatial correspondence. And this spatial correspondence, basically the probability distribution, is used to compute the soft correspondence loss. And we minimize everything end to end. So here, basically, we need to backpropagate through pseudo-inverse if we compute the functional map correspondence in closed form. You see that it's pseudo-inverse of f that depends on the parameters theta. So basically, we need to have a differentiable. Fortunately, frameworks like TensorFlow allow to do it. So probably it would not be an easy task a few years ago. But now the framework is very well developed. And this is the result that we get. We call this functional map network. So this is work of Litani and a few other people. You see that we almost saturate the Faust benchmark. So this is almost perfect correspondence. Okay, how much time do I have? A few minutes. So I will try to wrap up as quickly as possible, and then we'll be happy to answer questions. So basically, so far we talked mainly about shape analysis problems, right? So basically finding correspondence. Now let's say a few words about shape synthesis. This is actually a much harder problem and largely an open question, at least regarding intrinsic architectures. So imagine that I give you this noisy input scan that has missing parts, all kinds of noise. And basically we've seen that with intrinsic deep learning we can find the correspondence of this partial scan to a reference shape, right? So now what I want to do is to deform this shape in a way that will match the input 3D scan. Okay, so the question is how to do it. And this is our CVPR work from this year, also authored by Litani and collaborators from Google. Basically, we use a variational autoencoder architecture, intrinsic variational autoencoder. Basically, we encode our shape to produce some latent space, so a vector space representation of the shapes. And then, basically, this is the encoder. The decoder goes from the latent space to the shape. What is important that we assume that the connectivity here is fixed. So that's why it's limited to, let's say, human shapes. If you want to deal with animals, you will need to train a different model. Right, and basically when it comes, for example, to find correspondence with, basically to do completion of a shape, so here the input is denoted by this red. Basically we throw away the encoder, we use only the decoder, and we do optimization in the latent space. Basically what it affords us is that by virtue of the construction of the latent space, it already has incorporated some prior about how human shapes look like. So basically, the way that this latent space is constructed is actually linear operations, at least at small scale in this latent space, produce meaningful shapes. So you can do, for example, the standard things, you can do interpolation or extrapolation of shapes, or you can do arithmetics of shapes in the latent space. This is how shape comparison, completion looks like. So this is the input, this is the ground truth. This is, for example, how the Poisson reconstruction looks like. This is the work of Angela Dai and Matthias Niesner. Produces quite bad results. This is what we get with variational autoencoder. So it's not perfect, but it's much better than other approaches. So here are some real data. So this is Kinect data from a Berkeley dataset, and it works pretty nicely. Here's another example. This is Faust scans, and it also works pretty nicely. So maybe some fine details are not perfect, but this latent space has just maybe around 100 dimensions. So basically, we really capture the essence of shapes in a very small number of parameters. Now, to summarize this class of architectures, basically, what is good about intrinsic deep learning that the architecture itself actually incorporates deformation invariants by construction to the architecture. As a result, we need vastly less parameters compared to the traditional Euclidean architecture. So in the shape correspondence example that I showed, if we compare the Euclidean architecture image-based that was used by Hao Li, which had 200 million parameters and 50 million learning examples, here we had a few orders of magnitude less parameters and just 80 shapes on which we trained. Basically, we didn't need to learn any deformation invariants. That was the huge part of the training set that they had to use. So this is in general part of a bigger trend of deep learning on non-Euclidean domains, especially on graphs, as I mentioned in the beginning. There are several ways of defining intrinsic convolution. It's one of the main disadvantages actually of this this approach, that basically it's pretty exotic. You cannot immediately apply standard constructions that you use for images to meshes. And I think it has not yet become mainstream. Probably there is a lot to do to make it more accepted in the community. But I think, at least for some types of applications, that's the right way to go. Because it's efficient, it's accurate, you don't rasterize or you don't approximate your shape. It's automatically deformation invariant. Basically, you need to live somehow with these non-standard operations. So just before finishing, I would like to draw your attention to another tutorial on deep learning for graphics that was organized by Niloy Mitra and co-authors. Actually, I took, with permission, a few slides from his tutorial, so you can find it online. Basically, it covers a broad topic of the use of deep learning in graphics applications, including applications in rendering and simulation. And I advise you to consult it. We also had a tutorial with the Stanford people, with Hao Su and Leo Gibas and others at CVPR last year. So 3D deep learning, it covers more in-depth some of the volumetric point-based and image-based architectures that are briefly mentioned here. And finally, we had a very large and highly successful, I can say, at least judging by the number of people. It was attended by almost 3,000 people at NIPS. Tutorial organized with Yann Lecan, Joan Bruna, Arthur Schlam, and Xavier Bresson on geometric deep learning on graphs and manifolds, mainly focusing on graphs. So if you're interested in seeing that different perspective and different dimension to these problems, I suggest you to go to geometricdeeplearning.com, where you can also find a lot of examples of code, references, and so on and so forth. So I think I will stop at this point and will be glad to take questions. Thank you.
Oh, so the point that you mentioned, we use kind of the permutation invariant operation and then those shape functions to learn the features, but because we can also compute Partian and those diffusion distance on the point count, why not using the spectral method and the spatial method you mentioned for the meshes on the points?
Of course. So obviously, we have several papers from a few years ago where we show that we can use the same thing on point clouds. So to compute Laplacian on point clouds, usually you need to somehow approximate the local structure, either fitting some primitive or plane, or maybe some higher order primitive, or using a nearest neighbor graph. So you end up basically, instead of discretizing the Laplacian as a mesh Laplacian, you use a different type of localization, combinatorial localization or something like this. So everything will be the same. So we have results on point clouds as well. So the pro, of course, that it allows to easily deal with deformable shapes. So the architecture that I showed, the age-based convolution, basically it's a generalization of the localization. The local operator as a particular instance contains the localization. Yeah. But we have not tried it yet on deformable shapes.
Other questions here?
How do the results vary depending on the change of connectivity? Let's say we have two meshes with almost the same density, but we vary a bit the connectivity. Do the results that you have change a lot, or is it quite consistent with those changes in connectivity?
So because all the operations, so the question is about how topological noise affects the results. So because the operations are local, then basically the mistakes will be localized. So basically, if you have, let's say, fingers connected, then maybe the network will produce garbage around that point, but overall the results will not change.
Okay. And a second question: when you worked on point clouds, you talked about car nearest neighbors, and I wondered when you said between layers, you could you consider different. Not between layers. You consider different graphs actually that you recompute, and what about considering different keys for the same layer, but for different neurons? Let's say to not be biased by the number of neighbors that we consider. I don't know if something that you.
So well, k nearest neighbors is probably the easiest example for illustration purposes, but in practice we can use it. Basically, we can use some epsilon neighborhood, and actually this epsilon can be learned. So usually it's constructed as a Gaussian kernel on the distance matrix of all the pairwise Euclidean distances, and the parameter of this Gaussian can be learned. So there are many ways of doing it. It doesn't need to be a k-nearest neighbor graph.
Yeah, but then for the Gaussian, we could consider like more bigger neighborhood and smaller ones, and we can expect to find more fine features or more global features about the shape. So how do you choose actually for a specific purpose the good size of neighborhood to work
Sure.
on?
So basically, with the Gaussian kernel, basically there is no let's say hard definition of a neighborhood. It just decays to almost zero, significantly beyond its standard deviation. So if you add standard deviation as the learning variable, you will determine automatically during the learning process what's the right size of the neighborhood.
Okay. Thank you.
On the topic of learned shape descriptors, can you say something about how well they generalize to different kinds of shapes than those in the set they were trained on? So those which were generated from the human data set would have any chance of getting good results on mechanical parts?
Sure. So it obviously depends very much on the training set. So it depends on training set and the architecture. In general, the descriptors, if the network is not too deep and the patches are small, basically what the descriptors will learn is some kind of robust geometric primitives. So in principle, it should generalize across other collections, but mechanical parts, I guess, what you find in mechanical parts and what you typically not find in humans are sharp edges. So probably it will not generalize well to these kind of shapes. I don't know, we have not tried, but it is obvious that when you train on certain data set, you can fit to that data set, not necessarily overfit, but if you consider other geometric structures that, for example, have very high frequency features like mechanical parts, it might not work well. So in this case, you will probably need to include in your training set examples of such shapes. So in this sense, there is no magic.
Right. Thank you.
So I had a small question about MONET. So do you also use angular max pooling in the MONET framework?
So in the MONET framework, we used a canonical orientation. We used principal curvature. It was more or less arbitrary decision. We can also use max pooling, angular max pooling. So we've seen that there is not such a big difference between these. So for example, we are applying the MONET architecture to the problem of protein docking. There we use angular max pooling.
Okay, so I asked this question because if you use the principal curvature direction, then you have some ambiguity on the direction, I mean on the sign of the vectors.
Sure. So I admit that principal curvature direction was a cheap and dirty solution. It is actually, for example, in flat regions, you don't have a clear definition of principal curvature. So in that points, it can be more or less anything. Also, it's not intrinsic. So because we applied to human shapes are roughly articulated shapes. So if you ignore the joints, basically the principal curvatures are more or less fixed around the rigid parts, like basically the bones. So there it was somehow a justified decision. But in general, you should use something else, something that is intrinsic.
Okay, because for instance, in a CNN, it's not a problem because the filters that you generate will be symmetric, and even if you don't have curvature, then it will be even rotationally symmetric filters,
Sure.
I think. Yeah.
So you can use angular max pooling with monet as well.
Mm-hmm. Okay.
And you can actually see that the filters that we learn look symmetrically.
Ah, okay. Yeah.
You can actually force the symmetry.
Mm-hmm. Yeah, I see.
In the definition of the parameters of the Gaussian mixture.
Okay. Thanks.
So it seems that for the shape correspondence problem, you didn't use the localized spectral method that you introduced before. So is there any problem with that?
So well, we actually had. So the problem with spectral methods. So it's a little bit. Maybe I didn't make this distinction explicitly, but basically, what the spectral methods like the polynomial functions of the Laplacian. It's true that basically the motivation comes from spectral analysis, but actually these are spatial operations, right? You just apply the Laplacian, which is a spatial operator. So there is no explicit spectrum computation. So in principle, you can apply these constructions to computation of correspondence. I'm saying that you can do better. Basically, Laplacian doesn't account for directional patterns. So of course you can introduce anisotropy. We actually never tried spectral CNNs with anisotropic Laplacians. That would be an interesting experiment to do. But I think it's important to account for directions. We did it with spatial constructions. I guess you can do it with spectral as well. So it will probably produce reasonable results, but I don't know. We have not tried.
I see. Thank you.
So I can tell you what we have tried was localized spectral analysis, so windowed Fourier transform on manifolds. So basically it has basically it's projection on the Fourier basis, but it's localized with a window around each point. So this way, it's a spatial frequency type of representation similar to wavelets. So this works well for correspondence.